Welcome to JCon!
Welcome to JCon!
JCon, and welcome to my session on EclipseStore, Databaseless, Java Cloud Native Persistence for Microservices, and Serverless systems. So I'm super proud to announce that now at last, MicroStream is now EclipseStore, and EclipseStore is now available as a final release since last night. And at the same time, the MicroStream serializer project also is now available as Eclipse serializer as a final release. So now you can download it from Maven Central. Both projects are licensed as open source under the Eclipse public license. So now you can use it in production. And this session is all about EclipseStore. My name is Markus Kett. I'm CEO and co-founder of MicroStream. And we work with Java since almost 20 years now. We have been working on Java development environments. So we started with building a visual Java development environment. It's called RapidClipse. It is still available. So, and we worked with my team. I've worked on the JBoss Hibernate tools for Eclipse for many years. So we are very experienced in database programming in Java. And then we had the challenges that database programming in Java was mostly too complicated for our target group, for our users. And database applications through runtime were mostly too slow for our users. And this was the reason why we tried to simplify database programming with the JBoss Hibernate tools and to accelerate database applications through runtime. And then we tried a completely different approach. And so we started with the MicroStream project almost 10 years ago. And now it's an Eclipse project. So finally, EclipseStore is already part of popular microservice frameworks like Helidon. So it's already integrated with Helidon, which is a microservice framework. It's already part of Micronaut, and we have also integrations with other microservice frameworks, and more frameworks are using EclipseStore. So actually, the question is, what actually is EclipseStore, and why do we need another persistence for Java? So with all these modern applications with big data, with IoT, machine learning, virtual reality, blockchain, so the amount of data globally is exploding, and more applications produce and consume tons of data. And there are three critical factors for all of these applications in the future. So max performance, we of course want best possible performance, and at the same time at lowest data storage costs. So data storage costs are really critical. And of course, we want to have simple implementation for fast time to market, of course. And what we have seen in the past is that traditional databases, they, in comparison to a programming language, are slow, they are very expensive in the cloud, and they lead to high complexity. And this leads to expensive development processes, and it also accelerates the time to market. So the big question is, how can we simplify persistence and database programming in general? So with traditional databases, we have some challenges. So let's have a look on the architecture. Here you can see a traditional Java application. So everything is fine as soon as we do Java programming. So Java is object-oriented. All data are objects in the memory, and everything is very fast in memory. As soon as we want to store data, we are used to use databases. And of course, most databases on the market are relational databases. And the problem here is it's, from a technical perspective, a challenge to store objects, complex object graphs in a relational model, because of the relational model is incompatible with the Java object model. So we have really some challenges here. And with the modern NoSQL databases, we have actually the same challenges because of the NoSQL databases. Now they introduce new data structure or formats, but all of these data structure or formats are also incompatible with the Java object model. So we have the same challenges here as well. Of course, the problem is solved, and the problem is existing because of the relational model was invented in the 1950s, and the modern object-oriented databases came later, and Java came in the 1990s. So databases were already dominating the market. So it was obviously to store data, to store objects in a table, in a relational model, in table-based data structure. So in Java, it was solved by introducing object relational mapping. So Hibernate is here the major framework, de facto standard. So we have a layer in between the application and the database to make it possible to store objects in a relational database. And here the challenge or the problem is data have to be converted through every single read and write. So through every single write, we have read and write, we have to generate SQL code, and the results that have to be translated or transformed back into Java objects through every single read and write. And this is very expensive. This is leads to high latency. It slows down our queries, and mostly doubles or really triples the query time. So the problem is well known as impedance mismatch, object relational impedance mismatch. So to accelerate applications, we are used to speed up Java applications. We are used to use a cache. So what we're doing is we add a local cache. So then we can read the result sets directly from memory, and this should be much faster than hitting the database. That's cool. As soon as we are building distributed applications, this works fine. So as soon as we use distributed applications, then we have challenges here as well, because if we change data on one of our application nodes, then the application node and the database are in sync. But the problem is all the other nodes are not in sync with the database. So we have a problem here in terms of data consistency. So what we are used to do is we can now change our cache strategy and put the cache in between of the application and the database. So we run a distributed cache in addition to our database application. And here we can see the complexity of our system increases more and more. And it's the same with in-memory data grids or in-memory databases. You have pretty much the same architecture. And if the load goes up, then of course we need a third cluster tier. So we need a database cluster. We are used to replicate the database as well. So we run through 3 clusters in parallel. Here we can see the architecture of an in-memory data grid. So it's pretty much the same, as well as an in-memory database. So it's also an in-memory database cluster between the application and the database cluster. So this is what I meant with high complexity. It's because of we want to store some objects in a relational database. With microservices, we have now further challenges. It's because of there are some rules with microservices, and one of the rules is if you have a microservice that deals with data, it should have its own database. Imagine you have an application that consumes completely different data. So for instance, you have a microservice that consumes sensor data. You will obviously use a time series database. So, but if you have your relational database, your single source of truth, then you will keep an Oracle database or a PostgreSQL database. Then probably you have very complex data structure to process. Then probably you will use a graph database. So, and maybe you have some microservices that have to deal with unstructured data. Then you will obviously use a document base or a key value store. So multiple databases are used to run only one microservice application. So, and this again increases the complexity of your system because you have to run all of these database systems. You have to set up systems for the development time, for testing, and then your production system. So really high complexity and very expensive. And databases are really expensive in the cloud. Here is an example. So for instance, AWS, PostgreSQL as a service. It depends on the size of your machine, of course. Let's assume we need 250 gigabyte PostgreSQL as a service. It costs you around $3,000 annually. It depends on the size of your machine, of course. If you need 3 replicas, then your price will double, you triple, if you need more replicas for 6 nodes, you will pay around $80,000 per year. So this is the reason why I say this is very expensive in the cloud, and it's because of for running a database server, you need computing resources and storage. Storage is very cheap. Computing resources are very expensive in the cloud. Great thing is the cloud vendors provide very cheap data storages. So for instance, AWS provides S3, which is a binary data store, and 250 gigabyte AWS S3 costs only $70 per year. So much cheaper than a database. And there are some facts about Java. Java itself, we know it's super fast. So we have our JIT compiler, and the JVM can really outperform even C programs. We have the possibility to generate native images by using GraalVM, for instance. So we really can build super fast Java programs. So everything that's executed in memory is fast. So we talk about microsecond response time. Sometimes even nanosecond response time. That's really super fast in comparison to a database. Because of when we talk about the performance of databases, we talk about millisecond response time. And in Java, we have a great data model. We have the Java object model. And in Java, we can consume any data types, any data structure. So we can store single values, we can store single lists, maps, and also complex data like graphs, trees, or really graph with circular references. This is not a problem in Java. We can deal with vectors in Java, so this is not an issue. So it is already a multi-model data structure we have in Java from the beginning. So this is much more powerful than a database specific data structure or format, because the databases are limited. And so this is the reason why the databases are built for specific use cases. So they introduce and use specific data structure like a graph. So this is the reason why they are limited to the data structure and are limited in terms of the use case. And in Java, we have really a great query language. We have the Streams API. And this is fully type safe. Very powerful to search object graphs in memory in microseconds. So even if you search a huge object graph in memory with thousands of nodes, we can search it in microseconds. So microsecond query time in comparison to a database, millisecond query times, which means Java is around 1000x faster. So this is not only advertising, blah, blah. So this is really 1000x faster than a comparable database query. The magic question is, can we store objects in Java? No, this is not possible. There is no feature in programming languages to store objects as they are in memory, to store objects persistently on disk. So how could we make this possible without using a database? Many developers, so this was not our invention. So many developers told me already, I have the same idea years ago, decades ago, just serializing my objects to disk. This would be super simple because then I only have to deal with my classes. I don't have to care for a database, object relational mappings, cache configurations. I don't need this. So this is a great idea. And there is even an architectural pattern. It's called system prevalence. So the approach is just keep your data in memory, build everything in Java, and just create a snapshot of your system state to store your objects persistently on disk. But there are some challenges with this approach, and this is the reason why this approach is not really working in practice to replace a database system. So because of creating a snapshot of the entire system state is really expensive, and the RAM capacity is limited. What about transactions? What is if I change my classes? So schema migration. What about implementing serializable? What about performance? So there are a lot of questions, and this is the reason why this concept is not really used in practice to replace a database. So, but with EclipseStore now, we have solved all of these problems, and there are many companies out there. They use this this approach already for their systems. For instance, gaming companies or banking companies who need really best possible performance for their high-frequency trading applications or their gaming applications where really millions of players play at the concurrent in parallel on a server. So they have built such systems and use it already for decades. But the problem was they had to build an entire database, in-memory database system for their own, individually for their applications. And so this is very effortful and expensive. But now with EclipseStore, we have a framework. We built a framework for that. So EclipseStore, the initial vision was, I want to have persistence, but I don't want to care for persistence anymore. I want my environment to care for persistence. This was the initial vision. Actually, the hardware should care for persistence. And then Intel came up with persistent memory. This was a great approach to store data very easily by just using persistent memory. So this is also not very popular in practice, and it's because of persistent memory is expensive, and so Intel sold the technology. But what if the software platform, so the JVM, would be able to care for persistence? So, and this was our vision actually. So unfortunately, there is no JDK, no JDK project that cares for this approach. So, and this was the reason why we started our own framework, and now it's an Eclipse project. So, and it's very simple to use. So with EclipseStore, we add data storage to the programming language, to Java. And just to synchronize your application data with the cloud or with any binary data storage. So you can, of course, use it also on-premise hardware. So and this would enable you to process data in memory by using pure Java concepts. No more database programming. You don't need an external database system at all. And it works in practice for more than 10 years. So it runs in production already. So many companies use it already. And this is how it works in a nutshell. So EclipseStore is a Java native persistence layer. We call it Java native because there is no more external technology involved. So this is really pure Java stuff. It runs within your JVM process. It runs within your application or within your microservice. And it enables you to store any object graph, any data structure, any object model of any size, any complexity, into any data storage, into any binary data storage. And vice versa, it enables you to load subgraphs, the entire system state, of course, or only subgraphs dynamically, and restore your object references in memory when needed. So you can use lazy loading to just load subgraphs to keep hot data in memory, that you don't have to restore the entire system state. And we combine this with transaction safety and full consistency approach. And there are three main benefits of this concept. High speed. So we talked about microsecond response time, microsecond query time. Then second, lowest data storage cost, because now we are able to use cloud blob stores for storing objects persistently on disk. And we saw they are really cheap. 250 gigabyte costs only $70 per year, 99% cheaper than a database as a service. And simple implementation. Why? It's because of it's pure Java. There is no external database system involved. There is no concept you have to learn. It's just core Java stuff. So simple implementation, faster time to market. You can focus on business logic, and this is the philosophy of EclipseStore. It's open source. Of course, it's an Eclipse project, so it's under Eclipse public license. So you can use it also for commercial purposes. The code is on GitHub, and you can now download EclipseStore from Maven Central. It's just a dependency. All right. So how does this work? Back to our architecture. Here we can see the Java architecture, or the architecture of a Java application or a microservice. We have a object relational mapping framework like Hibernate. We have a local cache. We have objects in memory and JVM. And here we can see a database server, like a relational database. And when we have a look into a database, then we can see, of course, we have storage. We have a database management system, and a database management system, of course, also will load data in memory, will keep data in memory, will cache it in memory. So on a database server, you also need a lot of memory to have a performant database. And very often here, business logic is implemented, like stored procedures or stored functions. So, and now what we're doing is now we replace the persistence framework. So we replace Hibernate with EclipseStore. Hibernate or Eclipse Link or something like that. Or if you use a NoSQL database, there is no more data conversion, just replace it with EclipseStore. So with EclipseStore, we are now able to use our object graph in memory as an in-memory database. So we keep data in memory, which means we don't need a local cache anymore. So we can skip the local cache. So we remove complexity. And on a storage, in a storage layer, we don't need a database management system anymore. We don't need stored procedures or stored functions. We just need storage. So remove complexity on a storage layer as well. We have proven in performance tests that it's really up to 1000x faster. So you can check this out. And now let's have a look on how this works with distributed applications. So we can now also replicate EclipseStore applications or EclipseStore microservices by using replication. So we can replicate the system state. We can replicate the object graph through hundreds or even thousands JVMs. So in a distributed system, we can now replace the application nodes using Hibernate and the local cache. We replace it with EclipseStore nodes. As I mentioned, the object graph in memory is our in-memory database. We search and filter in memory. So in terms of replication, this works like an in-memory database and at the same time as a distributed cache at the same time. So we don't need a distributed cache layer anymore. So we can skip the distributed cache. And as I mentioned, we store data in a binary format persistently into blob store. We don't need a database cluster anymore, so we can skip a database cluster. And here is our simple architecture for distributed applications using EclipseStore. These application nodes or microservice nodes are now stateful. So yeah, you can use it in this way, but you can also use it as a separated, isolated cluster and combine this with stateless application nodes or microservices. So can also run your business logic with stateless microservices or stateless serverless functions, and just query the EclipseStore cluster by using REST or GraphQL. Then you can, of course, also use different programming languages, JVM languages, or also Python. But I guess this is not a topic for today. We are at the Java conference, of course. So this is simple, pure Java approach. Of course, there are some rules and challenges. So it's because of it works fundamentally different from the traditional database server paradigm. So it's a paradigm shift in database programming. On the left, we can see the architecture of a database server paradigm. We have a database, a remote database server. We query, so we call a database server, we query a database server. The query is executed on a remote server, and it sends a result set back to the Java application node. So with EclipseStore, the paradigm has changed. So your database is now within your application logic or your microservice logic within your JVM, and queries are executed within your JVM. This is, so keep this in mind. So there are no more classic selects. So you don't query a database system anymore. You don't query a database server. So you just query your object graph in memory. What about memory size? So if you have, of course, we talk about in-memory data processing, which means, yes, you should have memory, some memory. This would be an advantage. We have seen that we can skip a distributed cache, which means we save a lot of CPU power, a lot of memory. So put the memory in your application nodes or in your microservice nodes. Then you can run big memory machines. So if this is possible for you, you can load the entire database in the memory, and then this will be then you will have maximum of performance. Of course, here are also some cons because of loading the entire database in the memory will slow down startup time. So if you build microservices, this is probably not a case for you. So if you run big memory machines and so with big application, this might be not a problem. If you want to have small machines, micro machines, or even serverless functions, then this is also possible by using lazy loading. So then you can have a big storage and only some gigabytes memory. You just keep hot data in memory by using lazy loading. So how does this work? So actually, this is very simple. You just need a dependency, so include EclipseStore in your project, and then you need, of course, some classes. So that now the object or the data model is now so defined by your classes. So there is no more database model anymore. So just your Java classes, and there are no requirements to your classes. This is the cool thing here. You can just use POJOs. There are no design rules, so you don't have to implement an interface like serializable, because we don't use the Java serialization. We use the Eclipse serializer for serializing the objects to disk. So no interfaces have to be implemented. There are no annotations to use, no superclass. So you can just use plain Java objects. Clean objects, that's it. Then we need a database instance. And so this is some graphics here. So we need the EclipseStore instance and in memory. And then we need a storage. It's created automatically by the EclipseStore framework. In addition to that, we need a root instance. So this is also very easy to create. In the root instance, this is the starting point. It's kind of like a root instance, the root of a swing tree, for instance. So it's comparable. So this is the starting point of your database, and all objects that are reachable from the root can be persisted by EclipseStore. So let's add some objects here. And so this is the only thing you have to do for storing objects. You just have to call a store method. That's it. And you as a developer, you will decide when you want to store your objects persistently on disk. So you create a new object, add the object to the root object, and then call a store method, and EclipseStore will create a binary representation of your object, store it persistently into your storage. Let's create some more objects. Then let's call a store method, and then we will create another binary. So you can see all stores are appended to the file storage. And each operation will create a new binary in a storage. Even if you change objects or if you remove objects, the information will be stored appended to the file storage. So we never overwrite data in a file storage. All right, so you can add some more objects here. So, and each store is transaction safe. So this is an atomic all or nothing operation. And the approach, the method here is full consistency. So you can really expect that we call store method that's really executed and will be stored persistently on disk. If it fails, you will get an exception. So I mentioned already, it's the same with changing some objects. I change an object, reference, store it again, and then we will create a new binary in a file storage. And so this means the storage will grow more and more, but this is not a problem because we have a kind of like housekeeping process and garbage collector that cares for reorganizing and restructuring the data, so the binary files in your file storage. When you start an application initially, how does it work? So we now start the JVM, then EclipseStore loads the object graph information into the memory. And it only loads the object IDs. So only the data structure of your object graph is loaded. No data are loaded. And here are two different options. So you can load data as eager. You can define your classes as eager or lazy. If you use eager loading, then all data are loaded initially automatically. If you use lazy loading, only the object IDs are loaded into the memory. And through loading your object reference, the objects are merged into your object graph automatically. So you can see how to use lazy loading. It's just using a wrapper clause. And then we can have access to our object graph just by calling get methods. And this is the very convenient part of MicroStream. It fully automizes persistence in terms of I don't have to care for classic selects, what data is loaded into the memory. Just call your objects with get methods. If the object is already in memory, you will get the object from the JVM. If the object is not in memory, EclipseStore will load it. So this is very convenient. Just calling get methods, and then EclipseStore will load the object reference in the memory, will merge the objects into your object graph, so you don't have to care for object copies. So you can use object copies. So the API provides you an approach for using object copies, but it's not mandatory. So it's very convenient. Just calling get methods, and EclipseStore will load the object reference into memory. And don't have to be don't have to be concerned in terms of the memory so out of memory. It's because of the JVM cares for your memory automatically, but you have full control of your lazy references. So you can delete lazy references, to remove lazy reference from memory, to save memory. You can define timeouts or let JVM care for your lazy references. So this is very convenient, fully automated behind the scenes. As I mentioned, queries, you just use Streams API. That's a different topic. And also they change some objects. So if you change objects, call a store method, and then EclipseStore will create a new binary file in the storage. And if you change your classes, this is also covered by the framework. So as soon as I change my classes, then we will have two different versions of objects in the storage, and EclipseStore can manage this automatically. So when you load an object reference in the memory, then EclipseStore will automatically compare the loaded object with your class. And if you have changed your class, so you add fields, remove fields, change data types, something like that, then there is a heuristic that recognizes the changes and can fix this automatically. For more complex cases, you can define a legacy type map. And so this is very easy to use. And then you store your object again, store the new version of your object, and then we will have two different versions of an object in our storage. We have the latest version, and we have a legacy. We have an old version, so legacy object in our storage. And now you can define and decide whether you want to keep the older versions of your objects or let the garbage collector remove the older objects, the legacy objects, from your file storage and clean up your file storage. So, of course, I have this animated as well. So you can see a lot of legacy objects in my file storage. And now I let the garbage collector remove the older object from a storage. What about the use cases? So there are a lot of use cases because of we developed EclipseStore just for storing objects. So this is a very generic purpose. Of course, we had no specific use case in mind. So we just wanted to simplify storing and loading objects. But of course, it's suited for caching, searching in memory. It's great for microservice persistence because of you can use it also with Lambda very easily. So it's very cheap in the cloud. So it's really suited for microservices, fraud detection, high frequency trading applications, gaming, data analytics, and much more. Dealing with really complex data, for instance, graphs, circular references. It's perfect for really complex object structure with circular references. The more complex your structure is, the better EclipseStore is for using it. But you can also use it for just consuming sensor data. And the good thing is you don't have to make a decision. So whether you want to remove your entire storage stack and replace it with EclipseStore, you can do that. But in a microservice architecture, you can make this decision for every single microservice. So there are some services probably consume data from an existing Oracle database or PostgreSQL database. You can keep it and build and use MicroStream or EclipseStore just for some microservices that need high performance for caching, for searching, something like that. So you can really make the decision for every single use case. And by the way, it runs also on Android. So if there are some people building apps for Android, it's pretty much the same. It is the same library used on Android. You can build and use it for mobile and edge applications running Android. So MicroStream is now EclipseStore, so we are now finishing further development of MicroStream version 8. So all new features are now implemented within the EclipseStore project. Migrating is very easy, so we have a tool for migrating existing MicroStream applications to EclipseStore. We work on great features, so EclipseStore cluster, managed cloud service. We work on an index API in combination with a new fantastic map approach, EclipseStore for vector processing, so for using for AI machine learning purposes. So a lot of great stuff is coming up now, and we have further talks through the JCon conference, and of course on Thursday we have the EclipseStore Summit, so which is a part of the JCon conference. Yeah, here we will dive into deep, and you will everything about EclipseStore. So conclusion: there are three critical factors for all of these modern applications. High performance, of course, everybody wants high performance, low data storage costs, and simple implementation. In practice, we have seen in many projects that traditional databases cannot keep pace with Java, with the performance of Java. So they are slower. They are built for specific use cases. They are expensive in the cloud and lead to high complexity. With EclipseStore, you can now process data much faster in memory by using core Java technologies or core Java features. You can save up to 99% costs in the cloud, so storage costs, because of you can use just plain files, but you can also use the managed objects stores provided by the cloud vendors. And implementation is simple because it's core Java stuff. You can download this from EclipseStore.io. So final release is now available. Check this out and join us at EclipseStore Summit on Thursday.
All right, thank you a lot for all of your valuable insights. We have only 5 more minutes to go through some questions from the chat. Maybe we can start with the questions from the chat.
Yeah, there are. I've seen. Yeah, there are really a lot of questions. So I will stay. I will stay here and answer the question in the chat. So, for instance, a great question here. So, is there a way to search to query POJOs in an SQL-like way? I don't know. I didn't find something, but this would be super interesting. So we are already have discussions on this topic. So if you have information about that, please inform us. I have no idea whether something is existing or not. I have no information so far about this. What happens if two services instances modify the same object at the same time? Very good question. So this you have to care for concurrency. So this is one of the challenges with EclipseStore. But you can use all approaches that are provided by Java. So you can use all concepts for concurrency handling, and it's up to you. But you have to care for that. I guess there should be some kind of synchronization between those two atomic operations. Okay, this was it's already answered. Can you unload objects to the memory to save memory? Yes. So you have full control of your lazy references. So you can clear lazy references in the memory. You can define timeout, or you can let the JVM remove objects that are not used to save memory. Yeah, so all of these functionality that it's provided by SQL, you have equivalent functions with JavaStream's API. You can search and filter. As I mentioned, you can use indexes. You can use Lucene. We come up with a specific index API. So you can, in general, use everything that's available in the Java ecosystem. So you can use and combine it with really all Java libraries. It's the only thing what EclipseStore provides is we store and restore. You store your objects, reload your object, and restore the memory. So you can really combine everything that's available in the Java ecosystem. You can store any Java type that can be restored in memory. GraphQL, yeah, you can also have access to your storage data by using our viewer. We have a REST interface that enables you to browse through your storage data. There is a CSV import export, and to let third-party applications have access to your EclipseStore application, you can use. You have to define interfaces for that. So you can use GraphQL or REST to let third-party applications have access to your application. Where are the slides? Oh, I will provide the slides immediately, promise. Okay, that's it for today. Thanks for joining and have a great day at JCon. Thank you very much. Have a great day. Bye-bye.